Let's discuss modeling artificial neural networks. Before that discussion, we shall understand why we need them and why we don't just work with, say, a logistic regression model like this one or a softmax model. Let's take the example of the AND gate. Say we have this AND gate and we have this plot that's for the AND gate. When x1 equals 1, x2 equals 0. So for at this point, x1 equals 0, x2 equals 1, we are at this point. x1 equals 0, x2 equals 0, we are at this point. Now this yellow means the output is 0, and this means the output is 1. From this, we could easily create a logistic regression model which does something like this. So it carves out all this portion, that is, it considers that all values around this region have an output of 1. So with a logistic regression model, we could do this very easily. If we want to use our logistic regression model to model the behavior of a XOR gate, we'll have this inputs from the XOR gate. So we have the 0, 1. So we have x1 equals 1, x2 equals 0, x2 1, x1 0, x1 1, x2 0, x2 1, x1 0, x2 0. We have that. For us to get this right, we'll need a model which is able to know that this point is a 0 and this is 0. It happens that with logistic regression model, we can't actually model this kind of information. So no matter what value we select for theta 0, theta 1, and theta 2, we won't be able to come up with this kind of function which can separate this region such that these two inputs are seen as an output 0 and these two as output 1. Hence the need for a model which can understand this kind of more complex data sets. So with this, we introduce you to neural networks. Instead of just taking our inputs, as in this case, and just having one output like here, we add up some layers before the output. Now the reason why we're adding up these layers is to create an output which is a more complex function, since some layers have been added. And because we have a more complex function, we will be able to model more complex data sets like this one. Now let's look at a simple neural network. But before looking at it, let's see what happens when we use a neural network to model this kind of data set. When we pass these inputs to the next layer, we have a whole new set of inputs. So we could look at this as input 1 and then input 2. So what the output sees here this time around is not this input 1, but this input 2. And what happens now is this input 2 takes this input 1 into a whole new space or a whole different set of values. So looking at this plot, for example, we have these two values here and here, which can be taken to this new position. So we have these 2 points here, and then these two values taken to this other position. We see that with values or with these points in this new space, we could basically do something like this, or create a boundary between the two different types of data very easily. So the job of this new layer is to take this input into a new space, which will make our model better understand this input data, because sometimes our input data has certain hidden properties that have to be understood by passing them onto other layers. Generally, we call these layers hidden layers. Taking a closer look at a neural network made of input, a hidden layer, and an output, we have many more weights. and biases, unlike if we had a logistic regression model. Now, those weights are noted from their origin to where they end, or their destination. So our origin here is the 0th point, and our destination is the first. So we have theta 0,1, and then our origin 0, destination 2, theta 0,2, origin 0, destination 3, theta 0,3. And then when we get to x1, our origin 1, destination 1, theta 1,1, origin 1, destination 2, theta 1,2, up to theta 2,3. And thanks to these many more weights, we are able to model more complex problems. And as usual, we always add up these biases. We saw on the linear regression why biases were very important. Here we have a typo. This should be theta 0, theta 1, theta 2. So this theta 2 is here, and then theta 3. Anyways, we are going to see other examples, and you should understand again better by seeing many other examples how these neural networks are constructed. Our next problem, our next dataset, is the dataset which composes of several inputs and an output, which is a particular letter of the alphabet. Now, to build such a neural network, as we can see, we have these 16 inputs, x1 right up to x16 with a bias. And then they get into one of these points. We could construct the rest, and we have this. So we have the 16 inputs. We've decided to have this hidden layer made of 3 hidden features, and then with the bias, and then the next hidden layer again. So unlike this one where we had only one hidden layer, we have stacked 2 hidden layers before the output. So here we have this 3 hidden features which we get from our inputs, and then again we have these 4 features with the bias which we get again from this hidden layer. And finally we have the output, which could be an A, a B, a C, D, right up to a Z. Let's not forget that with such problems we have a one-hot representation of each of these letters of the alphabet. So here we have our hidden layers, the input and the output. Then the number of parameters, we have the number of parameters for the hidden layer and the number of parameters for this. Now, how do we calculate the number of parameters linking the input and the first hidden layer? Now, our input is made of 17 different values. So here we have 17 times 3, because we have 3 different values or 3 different positions in this hidden layer. So that's how we have 51 parameters. Similarly, here we have 3 times 3, that's 9 parameters. And if you count, you have 1, 2, 3, 1, 2, 3, 1, 2, 3. Summing this gives you 9 parameters. For the hidden, in between the 2 hidden layers, we have 4 inputs and 4 outputs. So instead of this 5, here we should have 4. And hence we have 16 parameters. While here we have 4, or rather 5 inputs and 26 outputs. So we have 5 times 26, 130 parameters. Hence the term deep neural networks. Now the term deep comes from the fact that we have many more hidden layers when working with neural networks. So if we stack up, say, 20 hidden layers again, so we have this layer, we have the next and next and next up to this. So we have, say we have 18 layers in between this layer and this layer, then we could say that neural network is deeper than this one with just 2 hidden layers. And then this network with 2 hidden layers is deeper than this one with just 1 hidden layer. So that's where we have the name deep neural network. And this complex nature, or this more complex nature of this kind of neural network as compared to a softmax network or softmax model permits it understand better the inputs or the data set we have at hand. So we shall see in the practical section how when we had the softmax, we had a loss which ended at 0.82. We had 0.825, 824 values like that. But now with a neural network with just even one hidden layer, we are going to be able to take that loss from 0.8 to a value even less than 0.1. And that's simply because this kind of networks or this kind of models are better placed to understand such data sets. It should be noted that the term model is same as function. So basically, we're calling this deep neural networks or models, but they are actually functions. So the difference between this and maybe this or a simple logistic regression model is that these are more complex non-linear functions as compared to, say, a softmax or logistic regression model. Although the way we get each value, say in this hidden layer, is the same as or similar to the way we get values in a logistic regression model, where we just simply take the weights and multiply by the inputs and then add them up to have the output. So in this case, for example, say we have this value at A, we have the weight which gets to this, the weight linking this one or this bias, and A, the weight linking this and A, all those weights which are multiplied by these inputs and then added up together to form A. So it's a similar kind of operation, but the difference is here is that these operations are stacked, leading to an overall function which is way more complex than the original function. For now, we've only spoken about the linear functions which are stacked to have this kind of network. What if we add activation functions, which are actually nonlinear functions? This is going to increase the complexity of our networks and permit us better understand patterns found in more complex data sets. The first activation function we shall be talking about is the sigmoid function, which we've seen already. We have there as x tends towards positive infinity, sigmoid of x, which is equals 1 over 1 plus e to the negative x, is exponential function. This tends towards 1, and as x tends towards negative infinity, this tends towards 0. When x equals 0, sigmoid of x equals 0.5. So that's why in all these different points we have a. This a stands for activation. So what happens here, for example, is to have a of x11, we first get x11. Now this 1 at the top, like at the power, tells us that we are the first hidden layer. Same with this, we are the first hidden layer, and here the second hidden layer. That's why we have 2 right up here, 2, 2, 2. And then there's 1 below, that's the subscript 1, tells us that we are at position 1, position 2, position 3. Now to have x11, what we do is we have theta 01 times 1 plus theta 11 times x1 plus theta 21 times x2, and that gives us x11. Once we have x11, we apply the activation function, which in this case could be a sigmoid function, and that gives us sigmoid of x11, which gives us the value we actually have at this point. The next activation function we could work with is a tanh function. This is a hyperbolic tanh function. You could go through our calculus course to better understand functions and how they plotted and their properties. With the tanh function, we have as x tends towards positive infinity, f of x or a of x is tending towards 1. As x tends towards negative infinity, a of x is tending towards negative infinity. But the difference is that when x equals 0, a of x equals 0. Our next activation function is the ReLU function, which stands for rectified linear unit. With the ReLU function, basically we have this y equals x when x is greater than 0, 0 elsewhere. Now, the ReLU function is advantageous in that networks which use more of ReLU as activation tend to converge faster than networks which use more of sigmoid or tanh function. Let's explain this point. Suppose we have the value of x strictly greater than 0, and as we approach infinity, we have this curve which slowly approaches the value 1. Now, if we take any point, say let's take this point here, we extrapolate to this point, the slope of this curve at that point is quite small, and because of these small derivatives, learning happens to go slower. So the model tends to converge slowly as compared to if we had a greater or a steeper slope as x is greater than, or let's say x is tending towards positive infinity. With the ReLU function, as x is going towards positive infinity, we have this linear or we have the straight line which maintains its gradient as we go from 0 right up to positive infinity. In this case, we cannot easily have the vanishing gradient problem as compared to this, where as we increase the value of x, our gradients become too small that we could face the vanishing gradient problem. And this leads to faster training as compared to these two other activation functions. Another important point to note is that with activation functions, we could basically use them in the hidden layers depending on our kind of problem. So we could decide to use ReLU or even sigmoid depending on our problem. Now, for the output layers like this or this one, if we are dealing with a regression problem, then we could comfortably use a ReLU function, as this output can take several values over a given range. But we may not want to use a sigmoid function as output of our network or our model when we are dealing with a regression problem, because our values will always range between 0 and 1. Now, for classification problems where we want our outputs to be between 0 and 1, that's where we could use the sigmoid activation or the tanh activation or even the softmax activation where we have a multi-class problem. Another variant of the ReLU activation function is a leaky ReLU function. Now, sometimes we don't want that when x is less than 0, our output should just be 0. Sometimes we want to have some little negative value. And depending on how big we want this negative values to be, we can tune the value for alpha. So leaky ReLU, if we have x when x is greater than 0 and alpha x elsewhere. Now here we actually have x greater than or equals 0 and here x greater than or equals 0, and not x strictly greater than 0 and here x strictly greater than 0. Let us take a closer look at these activation functions by studying their derivatives. We start with a sigmoid function. Say we have a equals sigmoid of x equals 1 over 1 plus e to the negative x. The derivative of a with respect to x is the derivative of this function with respect to x. Applying the quotient rule, we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. Hence we have this. So we have denominator times derivative of 1, which is 0, minus 1 times the derivative of 1 plus e to the negative x. The derivative of 1 plus e to the negative x is minus e to the negative x. You could check on our calculus course if you want to better understand this. Divided by v squared. So we have 1 plus e to the negative x, all of this squared. And next we simplify our numerator. This gives us e to the negative x divided by 1 plus e to the negative x, all that squared. Putting this separately like this, where we have e to the negative x divided by part of this, because 1 plus e to the negative x times 1 plus e to the negative x is what we have here in the denominator. And taking this separately like this, it gives us 1 plus e to the negative x minus 1 divided by 1 plus e to the negative x. Now, the reason why doing this is simply because 1 plus e to the negative x minus 1 is the same as e to the negative x. So we have rearranged it this way, and then we have 1 over 1 plus e to the negative x, which is still here. From there, we have 1 plus e to the negative x divided by 1 plus e to the negative x, which gives us 1. Then 1 divided by, or minus 1 divided by 1 plus e to the negative x, which gives us this. And if you look at this carefully, you'll see that 1 over 1 plus e to the negative x is a, which is our sigmoid function. So here we have 1 minus a times a. So that's the derivative of the sigmoid function. The derivative of the sigmoid is itself times 1 minus itself, which is this. We move to the tanh function. That's a hyperbolic tan function. A equals tan of x, which is equals e to the x minus e to the negative x divided by e to the x plus e to the negative x. Derivative of a with respect to x is given as this. And we apply the same rule. We have the denominator e to the x plus e to the negative x, which is this, times the derivative of the numerator, which is the derivative of e to the x minus e to the negative x. Now, differentiating this entails differentiating e to the x, which gives us e to the x. Differentiating minus e to the negative x gives us plus e to the x, or rather plus e to the negative x. That's why we have plus e to the negative x. So we have the numerator or the denominator times the derivative of the numerator, which is this, minus the numerator, which is this, times the derivative of the denominator, which gives us this, divided by the denominator squared. And simplifying, we have this times this gives us e to the x plus e to the negative x, all that squared, minus this times this, which gives us this, divided by this. Again, subtracting, or first dividing this with this, we have 1, because it's the same, minus e to the negative, or e to the x minus e to the negative x all squared divided by e to the x plus e to the negative x all squared gives us this. Now, if you notice again, e to the x plus e to the negative x divided by e to the x plus e to the negative x, all of this squared, is the same as a squared. So the derivative of the tanh function is 1 minus the function squared. We move to the rectified linear unit. Defined as such, the derivative with respect to x is simply 1, because derivative of x is 1 with respect to x for x greater than 0 and 0 elsewhere. We move to the softmax function. Here we're working with ai instead of just a, or ai equals softmax of xi instead of just a. And this is because the softmax function is linked to other points. So it's important that we know on which point exactly we are working. Recall that if we have, say, 3 outputs, A0 or A1, A2, A3, we can have A1, which is the softmax of x1, which is e to the x1 divided by the sum of e to the xk, where k moves from 1 to 3. So which is e to the x1 divided by e to the x1 plus e to the x2 plus e to the x3. And that's why it's important for us to note the index with which we are working. That said, we go to find the derivative of ai with respect to xi. In this case, we're supposing that we're deriving this with respect to the point from which it was gotten. So I here is the same as this. We shall have another situation where we could have a j here and an I here. So we could derive ai with respect to xj, which is different from I. For now, we have ai with respect to xi. The denominator in this case is put here. We have the denominator times the derivative of the numerator, The derivative of e to the xi with respect to xi is simply e to the xi. Now, minus this numerator e to the xi times the derivative of the denominator with respect to xi. Given that this is a sum from k equals 1 to the number of classes, at only one point we have k equals I. Recall that if we have, say, 3 outputs, x1, x2, x3, then if we have I equals 1, then this is e to the x1 divided by e to the x1 plus e to the x2 plus e to the x3. So it's only at one point that we have k equals I, or k equals 1 if I is equals 1. That said, for the other sums, we have a derivative with respect to xi, which is 0. And we only work when we have e to the xi, or when k equals I. So the derivative of e to the xi with respect to xi is e to the xi. That's why we have this here. Now, all this divided by this denominator squared, which is this. Then we move on to rearrange this numerator and the denominator too. So we factor out e to the xi, and we have e to the xi times this, which is given here, minus e to the xi. We factored it out, divided by this times itself, which is simply the squared, which is this times this. And now rearranging again, we have e to the xi divided by this part, which is this, times this other part divided by this other part of the denominator, which is this. From here, we have this given here, and now this divided by this part of the denominator, which is 1, minus e to the xi divided by the sum, which is here. If you notice again, this gives us ai, because this is basically the softmax of xi times 1 minus the softmax of xi. So we have ai into 1 minus ai. This is very similar to the sigmoid's derivative. Here we consider that I and j are not the same. So at first we had these two which were the same, so we had basically ai, xi. Now these two are not the same. So here we have this denominator which is given to us. We have this denominator gotten from the square, because we have, if we are having this function here, right here, we have v, which is this is a here, du or du. So we're supposing that this is u, and then this is v. So if we are differentiating this denominator, or we are fixing this denominator and differentiating the numerator, we have this, which is here, times the numerator, or the derivative of the numerator with respect to xj. Deriving this with respect to xj gives us 0, because we are deriving e to the xi with respect to the xj. So here we have 0. Now minus the numerator, which is e to the xi, times the derivative of the denominator. Again, here we only have one of these values of k, for which we have k equals j. So in that case, we have the derivative of this with respect to xj, which is e to the xj and not xi as it was in this case. And all of this divided by the denominator squared. Rearranging again, we have this times 0, it's going to go off. We have e to the xi, e to the xj divided by this squared. And then we have minus e to the xi divided by this times e to the xj divided by this, which gives us minus ai aj. And with this, we conclude this subsection on modeling by understanding the derivatives of the common activation functions. It should be noted that there are many other activation functions, but these ones are the most commonly used.